Hey everybody, I hope you're doing great. Um, I'm doing pretty good. The lake is freezing, frozen one night, about an inch, a little bit less than an inch thick. That was it. Then it snowed. Then it leaked and broke, and water spouts, and then it had ice roads on it naturally from the water. And now it looks pretty frozen solid. It's been pretty cold. We're having this Arctic blast. It's about. I wasn't planning on talking about this, but this is it's interesting. Allegedly. Um, it has been right like from 5 to 10 degrees Fahrenheit today. It's getting down to negative, I don't know, negative 8 or 10. It was negative 6 in the morning when the rest of the family got up. It's been about 10 degrees most of the day Fahrenheit. So the house stays nice and warm, so that's good. All right, so I'm going to show you a video in a minute. Um, but first, I'm going to talk about why I'm showing the video and how it relates. And there's also a little bit of meta in here in the sense that, meaning conversation about the conversation, uh, because this is the kind of thing I've been talking to Gary about over the years in science, and when he started developing his own scientific theory, is if we're doing philosophy of science, you get to start your own theory that has a certain gist, and it can be before a mathematician comes along, and that's all fine, but you should be discussing things with people. What the heck is causing this to go bright and dim on this screen? Some problem? Goes bright. My screen brightness is just changing like crazy on the laptop screen. It's driving me nuts. I thought I turned that off, and now maybe the laptop's dying. Anyway, getting down to the gist of it, it's like, what don't you like? And because I'm willing to share the knowledge in the sense of, helping to beef up your theory if it's something I understand. And one thing with Gary has been the idea that what you have is there's a weirdness about quantum mechanics. And there's some choices in the sense that something's very weird about it. One thing gives or another thing gives. And what Gary seems to be upset about is the particle can't go through both slits. It has to go through one or the other. So he prefers what has been you could call a hidden variable path in the sense that other people have also had this objection and they've thought up other ways. And this video I'm going to show you is about that. You might have seen it before. I think it's, a lot of people saw it. It's very cool as a metaphor. All right, about particle wave duality. Now, I can't wrap my head around exactly characterizing Gary's thing. To me, it's still like it has something to do with I don't like the double slit experiment, so I object to it, so fishes. So he'll say because you haven't watched closely, but I've watched a lot of your science videos. Okay, and that's not necessarily criticism. I will accept that, yeah, maybe there is actually more to your idea than I can understand so far. But some of it's because you don't actually haven't explained it to the level of um, philosophy of science. What's the real difference? And so I've tried to propose, I think, is it this, is it this, is it this? Here's things I can understand. There's a battle between realism and localism. You can choose various things. Um, well, realism versus locality. Basically, the major interpretations, like the loss of realism, is that we say that when you can't see it, the object isn't here or there. The cat isn't alive or dead. It's in a superposition of that and every other state of being sick and having the flu and not having, it's in every state. That's the loss of realism, right? Because that says that, well, it isn't really some way except for when you take the measurement, and that's the Copenhagen collapse, and that is kind of ridiculous sounding. So but the other idea where there is something real, then you lose locality, right? If with the loss of realism comes from the fact that the scientists sided with locality, that there was no spooky action at a distance, right? That the action is always nearby. To touch something, you have to be next to it. You can't touch something way across the universe. There is no astral projection. And so it turns out with the way the math works now, that to be compatible with the math now in the same way that relativity is compatible with and enhances Newtonian mathematics, to have a new theory that doesn't violate what we've already seen out of the patterns, in the mathematics that's pretty accurate now, sets up this problem between realism and locality. Either it's realistic and there's one particle, but it can influence places far away, faster than the speed of light kind of thing, or it's synchronized with those places, or um, it is things can only affect their neighborhood, but the things are superimposed. They're multiple options at once. They're the qubit, where they're the electron that has up and down spin, both polarities until you check kind of thing. Right. So, a major idea in quantum mechanics that isn't the popular one among scientists, but it's also, not scoffed at, and people still do look into it. And this video will show you too a good metaphor way of thinking of it. That and it's easy to think about because it's a realistic realism, and applying the metaphor. And that's the idea of pilot waves. The idea that, yeah, there's one photon, it goes through one slit or the other, but it's following on a pilot wave. And what was proved, was it Bohm or someone? What was proved was that if there's a pilot wave, it involves a couple problems, which, not problems, but, weird parts that you have to be willing to accept, which is there's hidden variables, and the pilot wave itself, defies locality. It's like it starts here and is a standing wave throughout the whole universe. Right? If you know what a standing wave is, you have to start them, and it takes a while if they're in the real world. And once you have time, then everything's going in this synchronicity. The wave is everywhere, and parts are just going up and down. It's a standing wave, they call it. And so that's what violates locality, is that this wave that is the pilot wave of a particular particle, and every particle has its own pilot wave, and all the pilot waves would somehow exist at once and throughout the whole universe. Because the weird thing about quantum mechanics, this pilot wave basically ends up being able to communicate information from the future to the past, telling you, synchronizing where you go, because everything becomes very deterministic. There's no randomness. It's realistic. It's a realism, and there's no randomness. But to accommodate that, information has to come from the future so that it can coordinate, and all the things that do happen that we observe in quantum mechanics have to, be accounted for in such a theory. And so you lose locality. All right. And this video, this is what it is, though. It's a great visualization of pilot waves, and you can see how pilot waves could work and produce like the results you see in the double slit experiment. So it gives us a genuine choice. Some of us will prefer to hold on to the realism, give up the locality. Some of us will prefer to hold on to locality and give up realism. It's a very interesting dichotomy. Skeptics will try to, what's the balance where both of those are options? How is that like Cartesian and radial coordinates where they're both an option? What is that perspective? And just analyze that. And a lot of people will take realism and say locality is bullshit. And or take a look at it and go, realism's bullshit. And I think this video will help cut the one from the other, because it gives a really good metaphor for how a pilot wave would work and why particles can do seemingly random things and not travel in a straight line, and yet it be totally deterministic based on the bouncing frequency of a wave and the particle that's riding on the wave. So it's either no randomness versus no hidden variables, right? Or it's randomness versus hidden variables. You either get randomness or you have hidden variables, if you want to figure out something compatible with what we've seen already with our own eyes and senses and measurement devices. And even understanding there's room for misunderstanding how our devices work, it's clear to me, like 99.100% clear, that we have this choice. It's either randomness or there's a hidden variables. And the problem with the hidden variables thing is that that means there's a hidden physics, right? Like you could have a physics that no one could ever find out. It means that there's something guaranteed. Like I believe there's always guaranteed to be an unknown, but any part of the unknown could be discovered, right? We don't have an infinite energy to ever get to the point where we've discovered it all. That's a good thing. It means there's still things to discover. Curiosity is a healthy emotion, it means, unlike many of them that we've evolved. So that's something I like. I admit I'm inclined towards preferring that to be the case. It could be wrong, but I like that idea better than the idea that there's a hidden physics, that the universe works some way where fundamentally, even by theory, there is no device or no way to probe in and get that information. And in the end, to me, it doesn't make a difference, because I follow a principle of functional equivalence. Two things that act, behave in every way, they interact with the outside world the same way, but inside they're constructed differently, but they act the same way. They actually are the same, and we can't look inside. They are the same. So, if everything's deterministic but fundamentally is hidden, then that just explains what randomness is. It doesn't mean there is no randomness. It just means, well, randomness is determinism where you're guaranteed to not ever be able to determine it, the outcome. Okay, now I'll just show you this video because it's good. You should also subscribe to this channel.
Check this out. I'm using this speaker to vibrate a petri dish containing silicon oil. Now, if I take this toothpick and I make a little droplet on the surface, the droplet will stay there, hovering above the surface. The droplet is actually bouncing, and it'll keep bouncing for a very long time. Now, the reason for this is there's a little layer of air between the droplet and the surface, and the droplet's bouncing so rapidly that that layer never shrinks to about 100 nanometers, which is what it would take for the droplet to recombine with the oil. Now, every time the droplet lands on the surface, it creates a wave. But this is a special type of wave, driven by the vibration of the oil bath. It is a standing wave, meaning that it's not traveling out, it's just oscillating up and down. So the droplet makes the wave, and then it interacts with that wave on its next bounce. If the drop lands on one side of the wave, it is pushed forwards. And as long as the bounce of the droplet remains synchronized with the wave, it'll keep landing on the front side of the wave and getting pushed farther forwards. Droplets like these are known as walkers. The bouncing oil drops have been known about since the 1970s, but only recently has it been discovered that you can use these little droplets to replicate many of the strange phenomena of quantum mechanics. Now, obviously, this is not a quantum system. The droplets are about 1 millimeter in diameter, but you can think of the droplets like quantum particles, say electrons. One experiment that captures the key features of quantum mechanics is the double slit experiment. If you send a beam of electrons at two narrow slits, well, the electrons, rather than behaving like particles and ending up in two clumps behind the slits, they produce an interference pattern. even when you send each electron through one at a time. With walking droplets, the pilot wave goes through both slits, interfering with itself, while the droplet only goes through one slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling. In quantum mechanics, it's possible for a particle to get through a barrier that it wouldn't classically have enough energy to get over. This has been demonstrated with walkers by creating a shallow barrier under the surface of the oil. Usually the barrier reflects the pilot wave and its bouncing droplet, but in rare cases the droplet does cross the boundary. And the probability of the droplet crossing the barrier decreases exponentially with the increasing width of the barrier, just as in quantum tunneling. Perhaps the most surprising thing about these walkers is they exhibit quantization, just like electrons bound to atoms. Here the walker is confined to a circular corral. The droplet seems to move around randomly as it interacts with its pilot wave. The complex interaction between the droplet and the wave leads to chaotic motion of the droplet. But over time, a pattern builds up. This is the probability density of finding the droplet at any point within the corral, and it looks very similar to the probability density of electrons confined in a quantum corral. All of these similarities are no coincidence. The walking droplets actually create a remarkable physical realization of a theory proposed by de Broglie nearly 100 years ago in the early days of quantum mechanics. He postulated that all particles have a wave that accompanies them and guides their motion, and that wave is actually created by tiny oscillations of the particle. Now, this pilot wave theory was marginalized when the standard Copenhagen interpretation became widely adopted. The Copenhagen interpretation excludes...
Okay, that's enough. I am going on camera here. You don't want to be on camera? Okay. So, but I'm just finishing up. So, all right. So you can watch the rest of this yourself. That's the basic part I wanted to show. It is a good video. He does have some more interesting stuff to say on how this may or may not relate. And it's pretty much pro-pilot wave. Now, I've always thought the pilot wave theory was pretty good, but when people resort to it because they're trying to, destroy, hey, it's not weird quantum mechanics. No, you lose locality. So, and he talks a little bit about this, I think, I'm not sure. But you can easily find this. It's Veritasium, but also if you just say, is this what quantum mechanics looks like? Say Google, it'll come up with this. And so for the realists that hate this idea of a particle going through both slits, this is the strongest argument currently in that there is a mathematics with it, right? Unlike Gary's current proposition, this has an actual, it's so concrete that you can write the mathematics for it, and the mathematics just might be good enough. Now, I don't quite think so. I think he said it looks very similar to it. Yes, because where the droplet lands is related to the interference, but it isn't the same. Now, if you read online why scientists are not in favor, they'll tell you because of the loss of locality, right? And Einstein and many, they did not want to lose locality. You have to be near something to touch it and pick it up. The idea that you could pick something up that wasn't near you, what? They have generally not like that. But I don't think that's really why they don't like it. I think they don't like it because of the hidden variable thing. The idea of skeptical natural philosophy, what people have had in common, whether they believed fire was the basic element or water or ether or whatever they thought, is that you could find out, right? Things are not readily apparent to us, but you can find out. The world is not as it seems to be right now, but you can find out. And then the world won't quite seem to be like you think it is then, but some of the stuff you'll have figured out. Oh, the sun is a big hydrogen ball of hydrogen on fire. Okay. And you'll move forward. Now, there'll be more things you still don't know, but you'll be able to find out. Maybe you'll never find this out because nobody thought to look over there or care about that thing. However, you could. So a hidden variable where there's a whole system of hidden, because just one hidden variable means, well, how's that variable get set? There's a hidden system. It means there's a big hidden part of the universe. And not just hidden because our brains aren't smart enough, right? Because that's no big problem, because maybe we live another 5 billion years and our brains get bigger to evolve to handle the complicated ideas these current simple brains can't handle. And suddenly we'll be able to visualize things in 7 dimensions, right? At least theoretically possible. But no, a hidden variable is like, no, literally, this world cannot be affected by whatever goes on inside that, so it's like a black box barrier. I actually am willing to accept that, because really anything that's weird about the ultimate reality of the universe, that basically makes sense to me. But that's not what my like sensibilities, that's not what they go towards. Whether this intuition was built into me because of my own mental metabolism from the womb, or whether it's because of my experiences, whichever. I lean more towards the idea that, well, there's an infinite amount of knowledge, so of course you'll never consume it all. And even when you consume some knowledge about the universe, it's never complete. So there's always more you could go over and find out, and that's infinite. And thus, we'll never figure out all of it. But if we make a choice to learn more about this area, then we will. We can. And it's not theoretically limited by anything other than the amount of energy and time there is in the universe, right? Like by what you can learn is limited by your lifespan and your ability to, fly to Mars or not. But so it's bounded and limited, but it's not a hard boundary that you can never cross, like the speed of light or something. It's just you can only get so far up the staircase before it's a million stairs. Then you can only get so far before you just grow old and die or whatever, or run out of food if there's no food on the stairs. I don't know if there's food on the stairs. That's what I'm trying to say. All right, you might want to check out this video, and if you like this kind of, this is a pretty good science channel. All right. Oh wait, before I go, let me check. There's might be chats. Oh, there's some chats. More chats. I mean, I'd already commented. There was Nicholas DeSalencio and Devon Jones, and now there is Joseph Orlando. 5 billion years not likely, Joseph Orlando says. Well, I'm just saying in order. I mean, I just chose that. Did I say 5 billion? Not million? Because if it's 5 billion, I totally believe the human brain could get pretty big and be able to visualize 7 dimensions. Probably in 5 million, I would say. 5 million. Oh, the stairs. Yeah, yeah. Oh, there's no stairs? Well, oh. Well, okay, yeah, they're not really stairs, because you never know what's progress or upward. So that metaphor, you could call me on that. I would also could defend it. But in that case, I'm really just saying it's more like a territory, like the Earth, even which is finite, but an infinite Earth. You can never explore the whole Earth, but you can go anywhere within a great boundary. Like you could go very far away, but then your experience will be a skinny line going as far away as possible. Not necessarily more information than staying in the center. And it's a small area, but you cross over it many times. So that's all I'm saying. Yeah. Anyway, cheers. I love the fact that doing the videos this way, that I don't know how long was this one, half an hour. Yeah, 24 minutes. That's long enough for people to show up in the chat. I really think that's an interesting medium. Now, if they combine this with Hangouts, then you could go ahead and have people like, you know what I mean, bring people. People could, like, I could click on one of the chat names and there does a video call and they come up. I think that would be the ideal medium for the kind of whatever sort of a show these videos are becoming. Not mine, but I mean in general. The way I'd like to do this medium. But at least at least the chat already. I think this is a. I think YouTube's gotten to a milestone I actually appreciate because it's been about like 5 years of total degradation otherwise. No offense, YouTube. Thanks for the free bandwidth. But I will go, and I actually very much would like some of the people, um, Gary, if he's not going to call me dishonest, um, could call me wrong and other things, but if you're going to say that I'm not honestly telling you what I think, then, or what I think of what you've said and things like that, then you're not welcome in the conversation. But I would like comments on this because I think we've talked a lot about the quantum mechanics. I'm sure a lot of you who haven't commented and talked have seen this shit, maybe even hate it. But this pilot wave is something that it is appealing to me. I don't believe it. I think there's reasons to think differently. Some of the quantum mechanical properties being exploited in quantum computers become weirder. They could still work with the pilot waves, but maybe, I don't know, it does appeal to me. If anything, I sort of would like to think that because I really love when the metaphor is so geometric, like when you could think of, atoms as having shapes, like water is the Mickey Mouse molecule, and really, if you could see it, that is what it would look like. So, but I just think the many histories thing where you give up some realism is better. You keep locality, and everything is determined by the wave mechanics. And the appearance of randomness doesn't bother me because to me it's not like randomness. It's more like all of that stuff exists, and we're a cross section. Anyway, it just makes more sense to me. But I would love for one or the other to be proved, and I totally love like that graphic of a drop bouncing on a standing wave that it also affects and causes, right? Because what he goes on to talk about is how this process, every time that drop bounces up and down on the wave, it also makes another new little wave, which creates a memory so you can actually change the frequency, but bang, real quick, and cause that thing to go backward and trace its apparently random path, right? It'll trace it backward because of all the ripples on that wave are the silicon oil has, is very regular in its behavior. So all of the ripples that are on the wave from where it went can get triggered so that it'll bounce right back the way it came from. And anyway, whether it has anything to do with at all with quantum mechanics, it's a pretty cool phenomena. So I've been wanting to share that for like for a few weeks. So all right, cheers, you guys. The comments are also difficult because it's like, hey, what about this topic? It's like, well, I just made a half-an-hour video and it wasn't gonna make an hour-long one, but it's interesting. So cheers for now, though. Um, and again, yeah, I really like replies on this. Hi, Day, I'm thinking of you. Um, uh, I mean, I really was thinking of this as an example of something Gary should have listened to me tell him about the pilot wave theory. But you're a better example of someone that I'm curious. Does the pilot wave model, which is so well visualized here, and it's so hard to visualize the other models, does that appeal to you more? And that doesn't mean there's no space-time because the wave is happening in sort of the space-time, or no? Anyway, but also everybody, is this not possibly an appealing model in that we can actually visualize it, unlike the Copenhagen collapsey stuff or the many history stuff? Very hard to visualize how that's really going on. That's not a problem for me because I think this is how big our brain is. We can't just visualize every single thing in reality without a bigger brain or more time to arrange this one. So I'm not that concerned that it's hard to fathom. On the other hand, it is quite nice when something is fathomable and we've figured out a lot of things by sticking to what we can fathom. Dog, dog Toey bells. Can you hear that?